Some of you know what ClickHouse is, but for those who don't know, let me give you a quick overview. What's that? It's a very fast all-app database. It's LSM tree inspired, and it's extremely good at working with observability workloads. Why? Because observability workloads is lots and lots of ingestion. It's a constant ingestion flow. It's effective storage. And time to time, you query this data to get some output of your telemetry. So ClickHouse is really good at that. All the data that is being ingested is available right away for querying. Once you get the acknowledgement from the database that data was inserted, you can query this data immediately available. You don't have to wait for anything. It's true columnar data store. It has a fantastic compression. Okay. And it supports ingesting data at an amazing rate. Millions, tens of hundreds of millions, or even billions events per second. If you go to our website, it's packed with customer success stories showing how companies, bigger ones like Tesla and Anthropic, really pushed ClickHouse to its limits. Tesla was given a talk at our conference at Open House. They demoed that they achieved 1 billion rows per second of the ingestion rate. So yeah, it's a good choice for observability. And that's why we decided inside ClickHouse, build observability on top of ClickHouse. So let's look at some of the headline stats, starting with a number that's already pretty big, 100 petabytes. It's a lot of data that we're now managing. We're actually managing more than that. I think at the moment it's about 120, 130 petabytes already. Luckily, because of the good compression at the ClickHouse, these 100 petabytes of raw data ingested translates to roughly 5 petabytes data stored on disk, or in our case, in blob store. So that's 20 to 30 times compression, depending on what your data looks like. But what you can go around, and what is really mind-blowing for us, is that this data made up of 500 quadrillion rows. We have 500 trillion rows stored in the system that we call Loghouse. I'll get it later. But this talk is not about numbers. It's about the story of what happens when you are growing fast and existing maps are useless and you need to build a new one. So just a year ago, we published a blog post. We were handling 19 petabytes of data, which was already a lot. But guess what? This number just in a year has increased 5 times. You might have seen the name of Loghouse pop up here. That's actually the internal code name for our observability platform. ClickHouse, we love to combine words click or house in the names when we name stuff. We have Stress House, the performance testing framework. We have ClickStack, which is my colleague Mike is going to be talking a little bit later about our all-in-one observability product. So the observability platform is a Loghouse. Initially, we followed the conventional approach, as most companies do. We started building our Loghouse using OTel. It excels at achieving open interoperability. It allows you to receive logs, metric traces in various formats. There's a consistent processing. You don't have to lock into some observability vendor. You have the control over your data. And while OTel proved effective and made complete sense as a standard for almost everything, it became a bottleneck in our case. So let's take a look at what our OTel stack looks like internally. It's pretty standard architecture for OTel, and this is what our stack looks like. We are a KD shop. Everything in ClickHouse runs on Kubernetes. Kubernetes node is effectively just 2 instances, and our business as a company is running ClickHouse instances at scale. So you see there's like lots of different ClickHouses packed on the node. There is a OpenTelemetry collector in the agent configuration running on the node that tails the logs that this ClickHouse service produces, logs or like other telemetry. And then it packs it up, batches it, does a little bit of pre-processing, sends it to the collector gateway, which is the bigger OTel box over there. The job of that collector is to read the logs of the whatever agent sent him, batch them up, do some enrichment, some attributes transformation, and push it to the downstream to ClickHouse with a ClickHouse exporter. And then we're querying that. We use Grafana, we're querying it with ClickHouse SQL directly, whatever libraries you want to use to access this data, it's all available. We also use a HyperDX UI to query this data, and this is this, or as we call it now, ClickStack. So nice and sleek. Unfortunately, as always, it's not as simple. We run in multiple regions, and each region collects and stores its telemetry separately. Otherwise, we would have paid lots of cost on the network transfer between these regions. Also, there will be delays in data delivery because it has to go there, it has to be buffered somewhere. So essentially, we run a copy of the previous schema in every single region. And to query across the regions, we use the ClickHouse cluster functionality. And we can federate the queries across the different regional instances using the region as a shortened key. On top of that, we built the Grafana Scenes app that is aware of our topology. And when you query for some specific instance or pod logs and you specify the region, or it does the auto discovery for you, it just routes you directly to the local regional localhouse instance. So you're not fanning out your query to all of the cluster elements. So to understand the problems of OTel, let's look at this log staple course. It's the flow of a single log line as it is in OTel. Starting from the producer, ClickHouse converts its in-memory representation of the telemetry it wants to send to JSON, or to ClickHouse does it in JSON. You can do a protobuf, but essentially the easier way to do that in ClickHouse is JSON. So it converts it to JSON, writes it to standard output, container runtime, pipes from std out to file, like var log pod or something like that. Then OTel collector agent reads the file from the disk, translates it to OTLP representation. Then it forwards it to a larger OTel collector gateway. Gateway takes it, batches it, transforms it to the native ClickHouse format, does some enrichment, and batches it out, sends it out to the downstream ClickHouse server. Then ClickHouse gets this data, creates a part, and persists it to the disk. Every single step involves lots of cycles to burn, and we're just marshalling and on-marshalling data. And this has a critical problems at scale. Like, first, it's just wildly inefficient in our case. We're wasting so much CPU just transforming data over and over. And then you have the loss of fidelity. We had a ClickHouse at either end, the producer and the storage engine. And ClickHouse has a very rich data type system. So with JSON in the middle, JSON kind of forms like a lower common denominator, the lowest common denominator. You're not taking all the advantage that ClickHouse provides you with the data types. But the real killer for us was the data loss. The collectors can get overwhelmed. We couldn't keep with the assignment, so the agents ended up just throwing away logs. Telemetry was lost. There are ways how you can work around that in OpenTelemetry, but on our volume, you can, for instance, like put a message bus in the middle, right? But when you're pumping petabytes of data every day and lots of events, this is going to cost you. It's going to cost pretty significant number. So we needed to assign just more and more CPUs to the agents just to read the logs. And ClickHouse servers are very chatty. If you Google ClickHouse noise logs, why ClickHouse logs so much, you'll see a lot of complaints about it. It's a blessing and a curse at the same time. There's a lot of telemetry, but there's a lot of telemetry. So at one point, while on the bigger ClickHouse instances, a lot of CPU was just spent on tailing logs and processing logs. Something had to change. We needed more optimal solution, and we came up with a total rethink. We had to ditch the general purpose one-size-fits-all tool, which is OpenTelemetry, and build something really specialized for our case. We want to build a tool, does one thing, does it really good. And we built SysX. This stands for System Tables Exporter. And the mission is very simple. Get data from ClickHouse A to ClickHouse B, from one ClickHouse to another, as fast as it is possible. And the idea was to throw out all of the transforming in the middle and do all the enrichment and the transformations that we might want to do at the data gathering phase. And once we do that, it's just a literal byte-to-byte copy. So instead of this log-stackle course, we have this, basically direct streaming from multiple ClickHouse instances to a big ClickHouse instance. Pretty simple and elegant. Very simple example demonstrating how this idea works. We got two curl commands, one pipe to another in shell, queries one ClickHouse, returns result in native ClickHouse format. It's extremely efficient. It's binary, basically how ClickHouse stores the data on the disk. And then insert it into another ClickHouse. Boom, data's there. No extra CPU overhead on marshalling, demarshalling, and all the other stuff. Of course, we don't use curl. We're using Go ClickHouse library. It's open source, and we maintain it internally. But there was like few very interesting problems that we had to solve with this approach. And the first one is the dynamic schema generation. So the thing is that if we're querying the database directly for the telemetry that ClickHouse stores internally in the system tables, we replicate the exact schema from the source and we have to replicate it to the destination. So when some ClickHouse engineer adds a new metric, he creates a new schema for the system table. We take the schema, we add some metadata to it, like when we first encountered it, when we like a hash of the schema definition to distinguish them. Then we like enrich the data with some columns like pod name, region, CPU type, and whatever we want there. And we create it at the destination side. And now we have hundreds of tables. They're tracking the same metric log schema with just like minor changes. Like some metrics are there, some metrics are removed. It's here and there. So how we work around that? We work around that with an amazing thing that ClickHouse provides called merge table engine. The merge table engine just allows us to query this as all of these tables as a single table. It's not a merge tree tables, they handle storage. The merge table engine just uses regular expression to select the tables based on their name and the query's where clause. You see, there's like a name on the wildcard metric. Then it builds a view for the schema. It converts columns to nullable values for the columns that are like not present in some, but essentially does the union and gives you the unified view so that you can query and don't worry about the schema. ClickHouse is going to do that for you. That enables us to query many tables as if they're one. This is very useful beyond just dynamic schema generation. For large observability platforms that are built on top of ClickHouse, changing the data schema, like a primary key, for instance, can be very costly. Right? You need to rewrite the whole data set that you want. That gives you the tool to avoid that. You just create a new table with a new primary key, use the merge table on top of that, and it's gonna do and plan the query for you. So just a quick recap. We built SysX to replace the OTel, streamlining a multi-step process with a high overhead to pretty much a direct pipeline, which is much more simple and easier to manage. How efficient it is. Shipping 37 million logs per second we now ship 37 million logs per second with only 70 CPU cores with SysX. And with OTel, we were struggling with 8,000 cores for 2 million logs. And all of that was just like basically heating up the air because of all the marshalling and unmarshalling. But it's not just about shipping the data. Along the way, we found the immense benefits of using this system with all of our telemetry and really embracing the motto of store everything and aggregate nothing for high cardinality events. And now, how high is the cardinality that we're talking about? In ClickHouse, there is a table query metric log that keeps the history of memory usage, as an example, and metric values on a per query basis. Each query is unique. You have an ID, query ID, and then you have a 700 columns or 800 columns with different telemetry, different metrics. ClickHouse collected about this particular query. What aggregations were used? How long did it take to read from the block store? Was the cache used? Was it a cache hit? Was it a cache miss? 800 of them. And they keep coming. It's a lot of very fine-grained telemetry, but that makes our life as an engineers in ClickHouse much, much easier because we have a full view of how ClickHouse handled this or that query. And when customers come to us and say, hey, what happened? Why it was so slow? We can take a look and help them. Or another in-depth example. So the SysX scraper itself, there's an event that indicates just a record about what SysX scraper itself was doing. So we have status there. Was it a push, a scrape? What table we were looking at? What AZ was that? When it started? It shows that we scraped 120 seconds of data. It took us 0.05 seconds. We were running behind for 600 seconds. Is our target because different reasons. Exactly the start and stop times for a scrape. And we can examine this as a log series. You can see exactly the sequence of pushes. It's not particularly interesting when you start looking into problems or incidents that you're debugging. So how can you make use of it? How do we visualize this data? In the traditional approach, what would you going to do? You're going to start adding metrics, right? You're going to start defining the dimensions that you're interested in, like how long did it take for this AZ, for all the scrapers in this particular AZ to finish the scrapes, their rate of success, things like that. But why not just leave event as it is and just store it in ClickHouse and just treat it as a data problem? That's one view on this. Like you can examine the log line from the sysx exporter. You can see, for instance, like group it by the insert lag. And that it typically hovers around 10 minutes, which is 600 seconds, which is our target. But sometimes it spikes, and like that's an incident, and you need to like debug it. So you can look at this data like that, visualize the exact events individually. You can plot them on the timeline, and then you see that there's a continuous scraping pattern, then a brief pause, and then more scraping, and then brief pause, and then more scraping, and brief pause. Or we can chart it like that. So there's a wall clock of time of scrapes, considering the start and stop times in series. We can visualize the total amount of data scraped. And it's same metric. We didn't do anything. We just wrote a different query for that. This graph allows us to assess the lag for a single instance. So while most scrapes exhibit a similar gradient over 6 hours, that there's like a purple one in the middle that looks longer than others. So that gives us some insight already. But now, the screenshots that I'm sharing is from Grafana, but you don't have to use Grafana, right? If you don't have enough, if Grafana does not provide you with enough tools to plot and analyze data that you need, you can leverage any data science tool. You can use Plotly, a little Python script to generate and display the graph you want. And this version of events it reveals an anomalous pattern here. Like on the x-axis, there's a scrape time. On the y-axis, there's a wall clock time. And there was like a duplicate scrapes from a single instance happening there. That gives us the answer, what was wrong here. And really, we didn't do anything extra. We were just using all the data that we already ship and store in the system. How it is different from traditional metrics or Prometheus-like metrics. The traditional time series databases require you to accept the trade-off. Like you cutting the dimensions in pre-aggregating the data in a way that you, depending on your business case, that you think it's going to explode. But when an incident occurs, we often realize we're missing these crucial metrics. And I just went over the one of these incidents real quick. Didn't have much time, but nevertheless, I'll be happy to tell more after. ClickHouse offers a different approach to that by retaining the full data fidelity. And we call it wide events. And it's not a log, it's not a trace, it's not a metric, it's an event. Like what happened to your software, to your application. And on top of that, ClickHouse gives you the capability to query this data with SQL. And you can do whatever you want. You can use whatever tool you want. You can use whatever data science tool you want, whatever libraries you want. You have a lot of flexibility in that. So we treat observability in ClickHouse and observability data not as a metrics problem, but as a data science problem at data warehouse scale. We have hundreds of petabytes there. This talk is an abbreviated, like a short version of a blog post that we have. There's a QR code. It's a pretty long read with lots of technical details. But if you're interested, take a look at it to learn more about what ClickHouse has to offer for the observability. That's it. Thank you. I have a little time for questions.
All right. Any questions in the back here? Or in the front?
Hello. Yeah. It's pretty interesting the way you're solving the high cardinality problem, but a lot of the problems are with correlation. It's not within a single event context. So how does this architecture impacts the overall joining and correlation kind of things?
So ClickHouse being the OLAP database and the columnar data store, still supports joins, and we're working very hard on making them more and more efficient. The benefit and the way how we approach it is we store all the telemetry of like different subsystems of the ClickHouse in one database. So you really can just write a SQL query that takes data from the query log and matches it with the part log, and then matches it with the CPU usage, for instance, which is in another table.
But any significant benchmark improvement on those aspects?
Yes, I don't have it on top of my mind, but we do have a significant improvements on join performance. There is a open source benchmark. I look it up and I'll let you know